Alex.
Hello, Lauren. How are you?
Good. It's been a long day. I started at 10, 9:30.
Yeah, you had one this morning, right?
Right.
How did that go?
Wonderful.
Excellent.
Exciting.
Great.
Hello. Hi, Alex. Oh,
Hello, Lauren. How are you?
good.
Oops.
It's been a long day. So,
Now, this is how many have you done so far? I know this is this the last of the series? Lauren?
Hi, you mean the activity?
Yeah, the ASIAA Astronomers. How many? There's been several of them, I think, right?
Yeah. Actually, this is the last one.
Last one.
For the open house events.
Great. Unfortunately, Daniel says he's caught in traffic. So, he may be showing up at some point, but don't know exactly when he will be joining us.
So, Alex, you can host the whole event.
Yeah, great. Yeah, we'll manage. Keep
Good.
fine.
Thank you.
Oh, Facebook as well. Cool. Is there a link to the Facebook? I was having trouble finding it. Facebook video. Yeah, I got the YouTube. Okay, here's the Facebook. Got it. Says the content is not available right now. That Facebook link, it's a stream setup. It says that content is not available right now on the Facebook link. I don't know what that's about. Everybody's muted, of course, so just talking to myself. Lauren, I figure maybe we'll wait a couple minutes to give people time to arrive, but no, kick it off whenever you say. Got 5 people watching on YouTube right now. Hello, everyone.
I think we can start.
Okay, great. Welcome, everyone. Thank you so much for joining us here on a Sunday night here in Taipei. And my pleasure to talk to you all today. My name is Alex Teachey. I'm a postdoctoral fellow at ASIAA, Academia Sinica Institute of Astronomy and Astrophysics. And this is part of a series of Ask the Astronomers that they've been doing for Open House. And so it's my pleasure to talk to you today. Unfortunately, I can't speak Chinese well enough to talk to you all in Chinese about my research. Hopefully one day, but this is obviously going to be an English language talk. So we're hopeful to be joined by a colleague of mine, Daniel Harsono, who is recently a postdoc at ASIAA and is now a faculty member in Hsinchu. And I believe he has also still a joint appointment with us at ASIAA. I think he is stuck in traffic, so we will not wait for him, but maybe he will show up in a little bit later. But for now, I'm going to tell you a little bit about my research to start off with. And then from that point, I'm happy to take questions in the chat boxes. I'll try to watch those, or maybe Lauren or somebody can field those questions for us. So let's get into it. Let me share my screen and we'll I'll tell you a little bit about my work. Here we go. Oops. Just give me one moment. Sorry, folks. I reinstalled my operating system and now I have to set up all this stuff for the first time. Oh, goodness. I'm going to have to shut down Chrome for a hot second. So I will be rejoining you all in just a second. Please bear with me.
So Alex, just turn on your microphone.
Okay, hopefully you can hear me now. Sorry about the reboot. Like I said, my operating system, I had to reinstall my operating system, and now I'm doing everything, some things for the first time. Can you see my screen?
Yes.
Okay, great.
Exomoons. Mm-hmm.
Yes, so that is what I'm going to talk to you all about this evening. My work and the work of some of my colleagues looking for these things called exomoons. It's very exciting work. I think it's really awesome, and I hope you will agree. I hope I can convince you that this work is pretty cool and worth doing. And so let's get into it. And let me just say that I'm delighted to be able to do this work at ASIAA. There's not very many astronomers in the world who do this particular kind of research. And so I feel very fortunate that I've had the opportunity to come and do this work at ASIAA, and they've been very supportive, which I very much appreciate. So what are exomoons? Exomoons are moons of planets outside of our solar system, and we call those planets exoplanets. That's short for extrasolar planet, right? So we have, of course, 8 large planets in our solar system, and then we have discovered several thousand planets orbiting other stars, in some cases many light years away from us. And that work is really astonishing. It just started in the early 90s, so we're only a couple of decades into this research, but we have discovered, like I say, thousands of planets orbiting other stars. And there's a variety of ways that we go about doing that, and I'm happy to talk a little bit more about that later if people are interested. But what I do is look for the moons of those exoplanets, and we appropriately enough call them exomoons. So the next question is why? Why do we care about this? I think it's very important in any time we are working on anything, but especially in astronomy, where in this particular field, we are not inventing vaccines or curing some disease or building a bridge. Astronomy's payoffs, the things that we provide, are sometimes not so concrete. That's okay. You know, there's lots of things in the world that are that way. But we want to have a clear sense of why we are doing this work. So why exomoons? Why do we care about doing this? I think there's really lots of answers to that question. But one thing that I will routinely tell people is that when we are learning more about these exoplanet systems, they are, of course, very interesting in their own right. They're fascinating worlds. We've learned so much about these thousands of planets that we've discovered. But we're also learning more about ourselves. We're really also turning a mirror on ourselves and understanding which ways are we typical and which ways are we not so typical. What ways are we special? That is actually still very much an open question. And as we discover these planets, we understand more about our context, our place in the galaxy. In what ways are we ordinary? In what ways are we extraordinary? And when it comes to our solar system, of course, we see lots of moons. Mercury and Venus, the 2 closest planets to our sun, do not have moons. We have one very large moon. Mars has 2 little small ones. And Jupiter has lots of moons. Saturn, the same thing. Uranus, the same thing. We see a lot of moons in our solar system. And so the question is, will we find lots of moons in these exoplanetary systems? It's a reasonable assumption to say, yes, we probably will. But where will they be? What will they look like? How abundant will they be? That's an open question. And again, this will sort of help us understand more about how common or uncommon our particular solar system is in the context of the galaxy. One thing that astronomers are particularly interested in, and several people working on this at ASIAA, is these questions of planet formation and moon formation. How does it all come about, right? For a very long time, we only had our own solar system to study. And so we had a very sort of tidy picture about how it all worked. And then again, when we started discovering these planetary systems, planets orbiting other stars, we started having a more complex, complicated understanding of what's going on. And another thing that we are doing, and folks at ASIAA are doing, are taking images like what you see here. These are what are called protoplanetary disks. This is planets in the process of formation. You're seeing a star in the middle, and around that star is a disk of material. And we have good reason to believe that the planets are forming from these disks. And you can see, just looking at this picture, how different they are, one from the other. They all look a little different. Obviously there's some common features, but also there's a diversity there. And so we are learning more about planet and moon formation. By the way, it all happens at the same time. Planets are forming and moons are forming, all sort of in the early days. And so we learn more by looking at these images. But these are just a snapshot in time. These are, you might call them baby pictures of these planetary systems. When we find these other planetary systems, they may be several billion years old. And so that's a different snapshot. So it's almost like you are studying how a human grows up from birth to old age. You don't get to watch a single human grow up usually. You see some babies around you, and you see some teenagers, and you see some middle-aged folks and some older folks. And you get a picture of how people age based on lots of different examples. And that's sort of how we understand the formation and the evolution of these planetary systems. And like I say, moons are forming exactly, during the same time that planets are forming. When it comes to moon formation, there's really three major ways that we think this happens. The first is in an impact scenario. This is how we think we got Earth's moon, for example. A large object smashed into the Earth, blew material off, and that material subsequently reformed in the form of our moon. So that's the first way, impacts, like we're seeing on the upper right corner there. The second way is through formation in what we call circumplanetary disks. And this is very much the same way that we form planets. As I showed you a couple of slides ago, the star has a disk of material and the planets are forming out of that disk of material. Well, the same thing is happening when the planet is formed. There's a disk of material around the planet and the moons form out of that disk. And so there are two very similar sort of processes there. And this is how we think we got, for example, the large moons of Jupiter and Saturn and Uranus, for example, in our own solar system. And finally, the third major way that you might get a moon is through a capture scenario. So what happens here is that you have another object that is originally not bound, not connected gravitationally to this planet, but through somehow it is brought into the gravitational influence of the planet. It's pulled down into into orbit around the planet, and so it is a captured moon. At that case, it didn't start as a moon, but then it becomes a moon. And one very typical example that we show for this is Neptune's largest moon, called Triton. It is orbiting in the wrong direction. We call it retrograde. And it is tipped up significantly with respect to the equator of the planet. And so astronomers believe that this is a captured moon. So that's the three ways that you can make a moon. And now we think, talking about the history and the evolution of these planetary systems, we also have good reason to think that planets, where we find them today, is not necessarily where they were born. Instead, they were born some other place, still in orbit around the sun, of course, or around their host star, but not necessarily at the same distance. So they start in one place and then they migrate, particularly in the early years of their formation. And so imagine if you have a planet and this planet has moons, what happens during this sort of cosmic billiards? The planets are moving around, they're sort of jostling, gravitationally influencing one another. And so what happens to the moons in those cases? Well, we tend to think that once we start finding these exomoons, you will get you'll start to develop a picture of how this all is all happening. It's just one particular route in to interrogating the clues that nature provides to us. And then thinking farther down the line, we're going to be interested in really getting to know more about these exomoons. The moons in our solar system, the large ones in our solar system, are just as interesting as the rocky planets. We know the rocky planets are Mercury and Venus and Earth, of course, and Mars. Well, we have several of these moons, particularly around Jupiter and Saturn and Uranus. And these worlds are just as interesting, I would argue, as the rocky planets. And they are very diverse in their surface features. They're geologically active, means there's a heat source inside. We have a moon around Jupiter called Io that has these sulfur volcanoes. There's a lot of stuff going on with these moons. There's an abundance of water on these moons, in some cases even liquid water. And in one case, we know the thick atmosphere around Saturn's largest moon called Titan. So these, like I say, are real worlds that are deserving of exploration, and we will want to get to know them. And astronomers right now are thinking seriously about how we can study these rocky planets around other stars, these rocky exoplanets. And eventually we will really want to be thinking about how can we learn more about these exomoons as well. We have to discover them first. So that's what my job is, and the job of some of my colleagues. We have to find them first, and later we can study them. And this is, not next year. It's not in 10 years. We might be talking 20 or 30 years down the line that we will be trying to understand more about these moons. But hopefully we really are going in that direction. So it's a very exciting time to be working on this. And, I put it together. We've got all the ingredients. We've got liquid water in some cases. We've got atmospheres. We've got an active geological landscape. It's not a dead rock in space. There's really a lot going on with this internal heating. And put it all together, in some cases, it looks promising that you can have all the ingredients that you need for life. And that goes both for moons in our solar system as well as potentially moons in other solar systems. So not every astronomer, frankly, is very interested in finding life out there. But for myself, that is a very powerful motivator. And so that's, I think it's a big part of the motivation for looking for these moons. So how do we go about actually looking for them? I've given you all the motivations. What do we actually do to find these things? Well, the one thing you might say is, let's just take a telescope and, take a picture of these planetary systems, and we can actually do this in some cases. It's called direct imaging, appropriately enough. We point our telescope at the star system. We have to block out the light. If you're looking at this video right here, that big black circle in the middle is we're blocking out the starlight itself and looking at the light that we are receiving from the planet, which may be billions of times fainter than the star itself. So we'd have no chance of seeing the planet unless we effectively block out the light. But this is what we can do. And this is, very pixelated, of course, but this is, and it's a few years old, but this is really still basically the state of the art. This is about the best we can do. And movies like this really just take my breath away, that we can actually see a planet around another star orbiting. We can see it in motion like this. It's really an amazing thing. But unfortunately, with this sort of technique, we don't have any chance of seeing the moons, not in the near term anyway. Farther down the line, we may actually be able to do that. But right now, anyway, it's a little out of reach. So we have to come up with other methods. We have to get a little more clever about how we look for these things. So what we do instead is we look for these things called transits. So what is a transit? A transit is what happens when a planet passes in front of the star. From our point of view, you can imagine, a planet could be oriented in any particular way. So we have to have the geometry just right so that the planet is in line with the star. And so if we have that geometry correct, then we can see periodically the planet passing in front of the star from our point of view. And what that will do is it blocks out a little bit of the starlight, just a little bit. We're talking 1%, maybe 0.1% of the starlight. It's very slight in some cases, but we really are able to detect it. And so we see in this artistic rendering, this is not a photograph. If we could take a photograph like this, I would be thrilled. But this is, of course, just an artist's impression of what we're seeing here. But if you have a planet and the planet has a moon, then you can see that the planet will block out some of the light, and the moon also will block out a little bit less of the light. But they will both block out some light, and that is the signal that we will see. And so this is what the data really looks like. So what we do is we take a bunch of pictures of the star over and over and over and over again, and we measure how bright the star is. And so when the planet comes around, like clockwork, the planet has a 100-day orbital period. Then every 100 days, we will see one of those dips that we call a transit. And if the planet has a moon, then there will be a big dip from the planet, and there will be a smaller dip from the moon. And so that's what we're looking at here. Now, this is just a simulation, but you can see what it looks like. Now, these blue and red lines, these are the models that are fit to the data. If I took away those blue and red lines, you maybe would not think that there is any moon signal there. You can certainly see the dip caused by the planet, but not necessarily the dip from the moon. So maybe that gives you a sense of how challenging it is to look for these moons, because it's a very, very small dip that we're looking for. We have to do it very rigorously in a mathematical context, so that we're really sure that we're seeing this dip. It has to be statistically significant. But nevertheless, in some cases, we really can do this. And these are sort of the signals that we're looking for. And this particular kind of data is pretty cool, because it actually has 3 different signals all in one data source. So we have these transits, like I said, the transit of the planet, as well as the transit of the moon. We also have these things called transit timing variations, as well as transit duration variations. So what's happening here? Well, the moon is pulling on the planet gravitationally. Of course, the planet is pulling on the moon, but the moon is also pulling on the planet. And so what that does is that they really sort of orbit a common center of mass. And it is that common center of mass that travels on the orbit that we're familiar with. We call it a Keplerian orbit. It might be a circle, it might be an ellipse, but it is that center of mass that follows that perfect orbit. But the planet and the moon are both displaced from that center of mass. And so they're both going around that center of mass. And what that does is that when we see the transit, sometimes the planet will be on one side of the center of mass, sometimes it will be on the other side. And what that means is that these transit events do not happen strictly like clockwork, but instead, sometimes they start a little early, and other times they start a little later. And so we can actually measure this. We can detect this. That is called a transit timing variation. We also see duration variations, and that is because now it looks, from our point of view, like the planet is going across the star more quickly or more slowly, depending on the geometry. And so the duration of these events will also change as well. So if you have a moon there, what's really cool is that you can have these 3 different kinds of signal, again, all with this one data source, and we can infer the presence of a moon. It all has to be self-consistent if it's really a moon there. So that's what I do. I work with data from this telescope called Kepler and data from another telescope called TESS. These are both space telescopes. And I have also had the good fortune of using the Hubble Space Telescope. I proposed to make a particular observation, and we got 40 hours of observing time on Hubble to look for exomoons with this transit method. And so I'm happy to talk a little bit more about that if people have questions. But that's basically how we do it. We work with this data, and there's a huge amount of data to go through. And so that's the nature of my work, is looking for these signals. And so one way that I have been doing recently at ASIAA is using machine learning. This is really sort of exciting. In astronomy, we are using a lot of machine learning now for a lot of different problems. And in this case, what I've done is I've tried to use machine learning to look for lots of, there's a huge amount of data to look through, and we can't look at it all by eye. And we need some way of flagging which systems look good, which systems we don't need to pay much attention to, which systems basically look like they might have a moon signal in them. And so I've sort of turned to this recently to go through huge amount of data. In my most recent paper, we looked at 57,000 transit events with this machine learning algorithm called a convolutional neural network. And we look for the moon signals in this way. So I think this is going to be very promising in the future as we have even more data. We just get more and more data all the time. And so that's one thing that I've been working on at ASIAA. Another thing that I've been working on a lot is investigating the signatures of planets with multiple moons. So you saw before in the artist's image and in the simulated data that there's just a single moon in the system. And, if we look at Jupiter or Saturn or Uranus, they don't just have one moon. Earth, of course, has just one big moon. But these other planets have many more moons than that. So for a variety of reasons, up to now, we have just done a single moon when we model it, when we are sort of testing our model against the data. We've always just kind of assumed one moon. But for a variety of reasons, maybe that's not the best way of doing it. And so recently I've been looking at studying these systems with multiple moons. What kind of signatures might we see from that? And the thing that I'm sort of excited about right now is using this thing called microlensing. So we talked earlier before about direct imaging, and it's sort of exciting in the near future, but not right now. We can't really do much with it. We talked about transits. Microlensing is another really sort of exciting way of looking for moons. So what is microlensing? Microlensing, this is super cool. We know, thanks to Einstein and others, that gravity warps space-time, right? If you have a massive object, space and time are warped by this massive object. So what happens is that if you have an object with a significant amount of mass out in space, and it passes in front of a light source that is, very far beyond it, it will distort that light and actually amplifies it like a lens. It's almost like you're passing a magnifying glass over it. All of a sudden, you get a lot more light from this background object, and in this way, you can detect these objects that are serving as the lens, this gravitational object. And remarkably, you can see very, very low mass objects through this technique. It's called microlensing. We see lensing on a much larger scale. We'll see galaxies or whole galaxy clusters that cause a huge amount of lensing. And those are sometimes very, very obvious. It really looks like a giant lens on the sky, and that's really amazing. But we can, believe it or not, see this same sort of effect with very low mass objects, including objects that are smaller than the Earth. So that's great, looking for moons. The sort of what's really sort of exciting is, we can look for these events out in space, and we will see them, and we can see these objects like moons. The problem is that in most cases, these events kind of catch us by surprise. So we're out there looking for them, but it's almost like a supernova. You never really know where or when it's going to happen. You've just kind of got to stare at the sky and look for them. And then every now and then you will see a lensing event, and then you record it and you analyze it later. But in science, we always like to go back and check things, and you can't really go back and check these events. You just record the data as you see it, and then there's no possible follow-up because you can't actually see the object that is causing the lens, and it has passed by, and it is now on its way, and it will never come back, and we don't know where it's headed, and we don't know when it might cause a lensing event again. So we get the data that we get, and that's about it. But what's sort of exciting, I've got a new idea about how we might be able to predict these events and plan for them, and look for moons using microlensing, and hopefully be able to perform repeatable observations. This is sort of a proof of concept, and it's going to take some near future telescopes in order to pull this all off. So it's not something that we can do right now, and it's probably why nobody has really proposed doing this so far. But I really think it will be possible to look for these microlensing events and predict them in some cases in the near future. So I'm very excited about that. And again, that's work that I'm doing here at ASIAA. So that's all I've got prepared for you. I see it's already 7:35, so I've been talking quite a while. So I appreciate your patience. Obviously, lots more to talk about with all of this. But at this point, I'm happy to take any questions. So thank you for your attention. Maybe everybody has tuned out at this point. Did Daniel ever show up? I think Daniel is still missing in action.
Right.
So have we got any questions? Let me see. I'm trying to pull up the YouTube, see if there's any questions on here. Well, if there are no questions, we can call it a night. Lauren, any thoughts? What shall we do at this point? I don't see any questions. So thank you so much to everybody that has tuned in.
Okay, let me ask you a question.
Certainly. Yes, please.
Since exomoons is so rare to detect, so how do you know that's exomoons, not another small planet, exoplanets?
Yes, that's a great question. So exomoons are, we expect them to be abundant, but we don't know, right? That's the open question. So how do we know that if we see a particular signal, say with transits, how do we know that it is not another planet in the system, say? And that's a very good question. So we know, for example, that if a star system can obviously have more than one planet, right? So we can see transits from one planet, and we will see the transits from another and another, however many transits there might be for that many transiting planets. The TRAPPIST-1 system, for example, famously has at least 7 transiting planets. And so if you look at the data from that particular star, you're seeing transits all the time, and sometimes they're stacked on top of each other. And if you didn't know any better, you might say, wow, that looks like a moon, right? So that all comes down to the modeling, because a planet, of course, will more or less, have the same period all the time, except for these transit timing variations that make it happen a little earlier or a little later. And every planet, of course, is going to follow those same rules. So you might have a planet that's on a 10-day orbital period, and another one on a 15-day orbital period, and another one on a 25-day orbital period. And so you would want to see all of these transits, and you would know, there's a small planet here transiting every 10 days. And so you flag that and you say, well, that's not a moon because I know that that's a planet, right? And the same one for all the other planets in the system. So you would know then that because that thing is coming around very periodically, that's got to be a planet. It's not going to be a moon. The moon, of course, is going around the planet. So the moon transit will always be very close by to the planet transit. It might be in the transit itself, or it might be just a little to the side. And, that's not going to come around like a planet. It will come around only when the planet who hosts the moon, that's when you're going to see it. These transit timing variations, again, become very important, because you can imagine if the moon is from our perspective, the moon is leading the planet, right? So the moon is out front and the planet is coming in behind, then we should see the transit of the moon start first, and then we should see the transit of the planet afterward, right? So the moon comes in first, there's the first transit of the moon, and then the transit of the planet starts afterward. Well, we should also see a transit timing variation associated with that, because the planet is on that side of the center of mass, right? So the center of mass, we know when it should be transiting, and the planet should be late, right? So if the moon transit comes first, the planet transit should be late, and vice versa. And so again, like I say, that stuff should all be self-consistent. So that's very important. But then there's a whole bunch of other stuff that we're going to check too. We want to make sure that the star isn't doing weird things, right? Stars are not quiet. They have a lot of stuff going on. They get brighter and they get dimmer, some regularly, some very erratically. So we would want to make sure that what we're seeing there is not, star activity. It could be something weird going on with the telescope. Telescopes do weird things, especially in space. And so we would want to rule that out as well. And we'd really want to see multiple events. So seeing just one transit generally would not be enough for us. We'd really want to see multiple transits of the planet with the moon. And in that way, I think we would start to feel like maybe we really are seeing a moon. Only when we have ruled out other explanations would we really feel comfortable saying, yeah, I think moon is the best case. It's not that a moon is a weird hypothesis, but we necessarily want to make really, really sure that we're getting the right answer. And so we have to rule out all of the other explanations before we do that. Other questions? Minkai has joined us. Hello, Minkai. And Dr. Smith says, how to find out the trace of microlensing. Not exactly sure what that means. I'm not sure if it's referring to the work that I've been doing recently or to microlensing more generally. So maybe I'll just say a bit about microlensing. We have a telescope coming up in the near future, formerly called WFIRST, and has been renamed to the Roman, the Nancy Grace Roman Space Telescope. And this telescope will be staring particularly at, I think, the center of the Milky Way galaxy, looking for these signals. It's wide field. That's why they call it WFIRST, Wide Field Infrared Survey Telescope, I believe is what it stands for. And they stare at the center of the galaxy looking for these microlensing events. And there have been other survey missions on the ground looking for these things as well. And so like looking for supernovae, you just kind of got to keep an eye out and wait for them to happen. And when you do, you kick into high gear and you point your telescopes at it and make sure you get the best data that you possibly can, because it's a one-off event. And so like I say, you've got one shot at it. And so you got to do the best that you can. This microlensing has been used to identify exoplanets already. And what's kind of cool about these is that the exoplanet is inferred to be a great distance from their star. And so what's really cool about microlensing is that we can see these planets that we don't have a good way of seeing them in other methods. This transit method, like I was talking about before, it has to be, we have to be seeing it edge on. And it turns out that the farther the planet is from its host star, the more precisely we have to be seeing it edge on. Right. So once you get to a very great distance from the host star, your chances of seeing a transit of that planet is very, very, very small. So we have to have other methods for looking for this. So we will use something called radial velocity methods, another method that I didn't talk about, and also this microlensing, because then we can see these planets very far away. Because we don't have a chance of observing these things more than once, what it really is good for is developing a statistical picture of what these planets will look like. We see a lot of these events, and we start to catalog, what the population of long period planets, very cold planets very far from their star, what that population looks like based on this microlensing. Minkai asks, can moons have life? It's a great question, and it is an open question right now. We think planetary astronomers, planetary scientists who have studied the moons in our solar system think that there are at least a couple of places here in our own solar system where life is possible. The one that people talk about the most is one of Jupiter's moons called Europa. Europa is a moon that is covered in ice. But beneath the ice, the planetary scientists tell us, there is a global liquid ocean that may be 10 kilometers or more in depth. So a global liquid ocean, it's super exciting. Water is essential for life. And, ice doesn't really do the trick. Water vapor doesn't really do the trick. You really want liquid water for life. So if you can find liquid water, it's a really sort of exciting prospect that you can find life. Now, Europa is a very cold world. It's covered in ice, like I say. So it's not necessarily going to be the kind of life that we would find here on the Earth, right? Obviously, it would be something much more like what you would find, underneath the ice caps in the Arctic and the Antarctic, extremely cold water. But of course, it's liquid, so it can't be, super cold. It's got to be liquid beneath the ice. It is an open question whether or not, because we don't have all of the answers about how life formed on the Earth. That is a sort of a key question in understanding whether or not life can exist on these moons. Do you need something like a light source, like the sun, or lightning? The questions of how life arose on the Earth is an open question. Some people think life started in shallow pools. Other people suggest life may have started at these hydrothermal vents. Well, if it started at a hydrothermal vent, then maybe you could have something like Europa. You have these, what they call chemotrophs, or organisms that eat the chemicals that are spewing out of the bottom of the ocean. You could certainly have something like that on Europa. And so if that's the case, there might be life. There's another moon in our solar system called Enceladus, the very similar situation where, again, the planetary scientists think maybe these are good places to look for life. But it's not super exciting. I mean, it would be amazing to find life on these moons, certainly. But can we talk to somebody on Europa or Enceladus? Almost certainly no. So then the question is really, can we find life, more like ourselves, someone to actually talk to in these other exoplanetary systems? And then moons. This is another open question. Can you have a moon that really looks more Earth-like, right? That you have stable liquid water on the surface, that you have a thick atmosphere, that you look something like Pandora or Endor from Return of the Jedi? Can you have a truly habitable moon that looks something like what we have here on the Earth? Potentially. People think that may be possible, but we don't really know until we find them. But moons stand to potentially expand significantly the amount of real estate that is available in the universe for life to arise and to thrive. Great question. Okay. Let's see. Are there any other questions? Otherwise, we might call it a night.
So any question from students?
I see a question from Micha Chang, question for Dr. Harsono. Unfortunately, he's not here. So I can't, and maybe Lauren can answer that question anyway. It's about a ASIAA YouTube video.
Sure. Well, Alex, your background is kind of special, right?
You mean like how I got here?
Right.
Sure. Yeah, I'm happy to talk about that. I did have sort of an unusual path into this career because I started as an actor. Actually, I went to school to study theater at New York University, and I loved being an actor. I love the theater. But a few years after I graduated, I realized that it kind of wasn't the career for me. It's a great career, but it's a very challenging career, and you will basically always be looking for work your entire life and trying to convince people that you're the best person for the job, and financially unstable and all those sorts of things. So I loved being an actor, but the job of being an actor, I slowly realized was not for me. So I started thinking about what else I could do. And eventually I got the idea in my head that I wanted to be a physics teacher, a high school physics teacher. And so I didn't really have credentials for this. So I went back to school to study physics. And so I went to Hunter College in New York City, the City University of New York, and got a physics degree, actually a second bachelor's degree in physics at CUNY Hunter College. And from there, I started doing astronomy research as an undergraduate student, working at the American Museum of Natural History, again in New York City, as well as the National Radio Astronomy Observatory out in New Mexico. And that is the home of the Very Large Array, which you may have seen before. It's this array of 27 radio dishes, this large radio telescope called the Very Large Array. So I worked out there for a summer, and I worked, like I said, at the Natural History Museum in New York, and eventually applied to graduate school and was accepted, fortunately, to Columbia University. I'd been living in New York City for quite a while, and I was very happy that I was able to stay at Columbia and get my PhD there. So I was there for 5 years, and that's when I got involved with this work, looking for exomoons with my advisor there, David Kipping, who is really one of the pioneers of this field, frankly. He was fantastic to work with and very supportive. And after 5 years, I finished my PhD. That was last summer. And I was thrilled to get this position here at ASIAA. And I came here a little over a year ago. I started at the beginning of October 2020. And it has just been great. It's been remarkable living here in Taiwan. I love it here. And working at ASIAA is really is a great privilege. I really like it.
Thank you. You must have been studying really hard to get all this credentials and arrive here before arriving here.
Study I suppose so. I tried to, when I decided to go back to school, I decided I wasn't going to fool around. I was going to try to, keep my grades up and sort of keep my options open. So I did very well at Hunter College, grade wise, and got involved with the research. And like I said, and fortunately that was enough to get me into Columbia. So, yeah. And I've been very fortunate to work on exomoons. It's something that is a very small field, but it is a field that people get very excited about. It really gets a lot of attention from astronomers as well as the community. And so I have that to thank in part for being able to come here, because I think exomoons is something that is still very early, still not a lot of people working on it, but it gets a lot of people excited. So I'm fortunate about that as well.
Right. Any advices for students?
Any advice? Let's see. Just do the best you can. Grades, keep your grades up. If you're an undergraduate student, if you're thinking about applying to graduate school, if you're thinking about applying to grad school, I think you got to go in with your eyes wide open. And by that, I mean, really think it through whether this is something that you want to do or not. I had one of the benefits of my sort of strange path was that when I decided to go for this, I was really sure that I wanted to do it. Whereas I feel like sometimes undergraduate students have been sort of in this pipeline, and they've just sort of always known that this was where they were going to get to go. They go straight from undergraduate into graduate school. And then sometimes people get to maybe their second or the third year, and they're not sure that they really want to do it anymore. And that's very natural. It happens to a lot of people. But that can obviously be very challenging for people, that they built up to all of this, and they're not even sure this is really what they want to do with their lives. And that's fine too. You've got to follow what makes the most sense. What makes the most sense for you? For me, I went into graduate school saying, I might not be in academia forever. I'd love to be a professor one day, but maybe that's not going to happen because it's very hard to get that kind of job, frankly. And I guess my advice would be, or the way that I have handled it anyway, is to treat this as part of my life not just a holding pattern for my life to start later. So I have thoroughly loved my time as a graduate student. I love my time here as a postdoc, and this is just a part of my life to live and to enjoy, and we'll see what happens next. Hopefully, get another job. I'd love to stay in astronomy, but my dreams won't be shattered. My life won't be over if that doesn't happen, because it's all about the journey, or at least it's part about the journey and not entirely about the destination, in my view.
Thank you. Thank you for sharing.
I'm seeing myself on playback on YouTube with all my hand motions. I'm pretty animated. Okay, are there any other questions? We've filled most of the hour. I see 12 folks watching on YouTube. Hello to everyone on YouTube.
I'm sorry, I have questions.
Certainly.
First of all, thank you for this amazing lecture. I learned a lot from it. And I'm really interested in astronomy, but I'm not major in it. So if I want to self-study some knowledge in astronomy, do you have any recommendation, like books or website?
Let's see, books or websites. What can I tell you? There's fortunately an incredible amount of programming, on television, on Netflix, and increasingly on YouTube. It takes some time to find the outlets that really speak to you. And so what I have done, even now, I mean, this doesn't help me with my research necessarily, but I have found a lot of channels that really speak to me on YouTube, and I subscribe to them, and they are great. Let me recommend my own former advisor's YouTube channel called Cool Worlds. He has really built this YouTube channel into an incredible thing, over 100,000 subscribers, or maybe even, over 200,000 subscribers or something like that. He just started it about 6 years ago when I came, and it's an incredible outreach, and particularly astronomy channel. What I think is really kind of cool about his channel is that he, in a lot of cases, really brings you into the research process and talks about how you really do research. It's not just about the answer. It's not just about the facts, but it's how we actually came around to finding those things. So I can't recommend his channel highly enough. It's really a fabulous channel. So YouTube is just full of resources. For more astronomy, there's textbooks and everything like that. It's a little dry. When I was getting into astronomy, when I was sort of changing paths from being an actor into astronomy, I became absolutely obsessed with reading the books of Carl Sagan. And Carl Sagan is a famous astronomer. He had a television series called Cosmos. Even though it was made in 1980, I think it still really holds up today. And he wrote a number of books. He was a prolific author. And again, I think it's really a great window, and not just learning these incredible things about our universe, but also, kind of understanding the thought process of what it means to be a scientist. There's a couple of recommendations. I don't know.
Okay, so Cool World on YouTube.
Yes.
And what was the author's name again? Sorry.
Yes. Now, Carl Sagan. Yeah, he is a sort of a hero of mine, if there are such things. Carl Sagan was really a remarkable astronomer and planetary scientist, and unfortunately, he passed away many years ago. So he's not up on recent sort of discoveries. But his books, I would say, are just as readable today as they were when they were written. and he's a phenomenal writer. So that really got me really excited about astronomy. And of course, there's websites. There's Universe Today. There's space.com. There are places where you can go specifically for finding space news and really, so following the current events of astronomy. And I will put a plug in for this event that we host here in Taipei called Astronomy on Tap. Astronomy on Tap is this phenomenal program that exists all over the world. It started in New York City, and I used to be a host of the program at New York City. Then I moved here, and now I got involved with Astronomy on Tap Taipei. And so we've been on hiatus since May, since the start of the pandemic here in Taiwan. But coming up in December, we will start our monthly events again for Astronomy on Tap. So please do check us out on Facebook to follow the latest on the events that we have there, where we're always hosting. Well, we have games, we have trivia, and we have space news there. And then we always have a featured speaker, usually an astronomer, will come in and give a lecture about their particular work. It's always a lot of fun. So please do join us at Astronomy on Tap.
Okay, thank you so much.
Thank you.
Okay, so I'm sharing the.
Yeah, post this information on the dashboard so you can check the link for Carl Sagan and the Astronomy on Tap in Taipei.
Great. Thank you.
Yeah, so thank you very much.
So, anyone needs a QR code? Here is it.
So if no more question, maybe we end here.
Great. Yeah, thank you all again for joining us, and thank you for setting this up. And it's been my privilege talking to you a little bit about this work.
Great thanks to Alex and everyone. Good night.
Good night, everyone.
Thank you.